All right. Um, so again, right here is typical. We sub in a little bit of a acid information because we need to function and we need to be able to do things. Acids are kind of in everywhere. So first of all, the general template of an acid is HX, and lots of times they're in water. That's what that means, aqueous. Okay. Types of acid, we have both an oxyacid and we have a non-oxyacid. Why do scientists have two different classifications of acids? Well, it seems like unusual, in the sense like this is HCl and this is like HNO3. And both these guys are acidic and they can do typical acidic-like reactions. But this one here also contains oxygen, which means it can undergo what's called a redox reaction. So most people don't realize that that's a whole new branch of acid. So if you take concentrated acid off a table and HCl and you wipe it up with a nice dry, plush cloth, it just picks it up, and you don't. If you got a glove on, you don't even notice the difference. You do the same nice dry cloth, whip up some concentrated sulfuric acid, and the rag starts on fire. So this is just open. They've split it up because this guy has a whole new branch of reactions that it's possibly do. It's fascinating. But all right, quickly, how do I know if it's an acid? All acids follow the same template, which is HX. So every acid will start with an H and have an anion on the end here. So there's a cation and there's an anion. Okay, so it looks a lot like an ionic compound. But in some places we might even call it an ionic compound if in some circumstances. All right, naming method, oxyacid. All right, so it's going to be the root of the anion. Okay, root, and then we're either going to use ic or we're going to use um, aus. This is if the family is an 8 version, and aus if it's an 8 version. It should be reviewed. So this is going to be nitric acid, and this is nitrous acid. Why? Because this guy is nitrite. So I have to use the aus version. Non-oxyacid. Okay, this guy here is going to be following method just now this one doesn't change much. It's just hydro, and then we're going to have the root of the anion, and then ic acid. So this one never changes. Okay, so this is just going to be hydrochloric acid. Okay, now in this situation, all we ever do is change out is this piece here. So this guy is going to be hydrofluoric acid, hydroboromic acid. Okay, so acids are pretty much everywhere now. Then these non-oxy versions, there's not that many of them, and it's just my non-metals. And we do have N-cyanide, which is also non-oxy. That happens to work nicely in this area. So, oxygen, of course, is out. That would just be water. But when we write out an acid, this guy here, for example, would be HN -3 plus 1. So we charge balance. That's very similar to an ionic compound. So it's H3N, and it's hydronitric acid. Okay, so hydro nitric acid. Technically, if we had one of these acids, it's not in water, so maybe it's in a gas phase, we name it as an ionic compound. All right. All right, naming acids. There we go. So we got 2 pages here, the same thing. Very good. And there we go. There's all my answers. Okay. All right, a couple different ones for you to try. Okay. take a moment, give it a try. Notice here, I just highlighted the fact that we have multiple H's available. We have a term for this. It's called the number of hydrogens you can donate here. If it's 1, then we call it, which just means this is -1, +1. We call it monoprotic. If there's 2, meaning this is -2, we call it diprotic. And there, of course, are things called triprotic and polyprotic. Okay, so try those out. And do I have the answers here? I don't. Okay, so let's do them quickly here. This is hydrobromic. This is, again, acid. This guy is hydrosulfuric and acid. Flip it over here the way, everyone starts with an H. Okay, always. This is carbon 8. This is nothing, just nitrogen. So this is carbonate, which is CO3 -2, so I got a charge balance, and I get H2CO3. They use this a lot in soda to produce, it breaks down into carbon dioxide. And this is a -3 plus 1, the 3 goes there, which is H3N. That would be a triprotic acid, by the way. Okay. Anything else we want to do here? Quickly wrapping things up. So is an acid ionic or is it molecular? It's kind of, it's right in the middle. Whenever I name these things out, we got used to naming things in honors chemistry. We'll do ionic on one side, covalent on the other, and we'll put acids in the middle. As a gas phase, we would typically treat it as an ionic compound. But, you know, in an aqueous, it definitely has properties of both ionic compounds, all right, and it has some properties of molecular, because all of our oxyacids, for the most part, are families, which are polyatomic ions. So, for example, HNO3, that's going to ionize to form H plus ions, and NO3 minus. So I'd probably lean more towards ionic than molecular, but that's definitely a molecule here. Can substances be both ionic and molecular? Well, that right there. Okay, so it's got right there, again, if we drew this out, this is where you can draw a Lewis structure of this thing, which would show it as being H, nitrogen, oxygen, oxygen, and oxygen. They're indicating that as a covalent compound. Absolutely. All right. So it's got a lot of things where our models aren't holding up very well. Okay. So we name it as an ionic compound typically. If it's not in water, but we always name it as pretty much like an acid, and of course we draw a molecule, a model of it. It's typically as a molecule, so it's right in the middle. All right, and we are going to stop there for that moment. Thank you very much.